Hello, this video is the solution to question 2 of probability assignment from course HAP 719. The question is, the given data shows caloric intake and blood pressure levels. Assume that caloric intake up to 2500 is normal and above this is overindulgence. Assume systolic blood pressure above 130 is hypertensive and otherwise non-hypertensive. First, do a chi-square test to see if caloric intake affects systolic blood pressure. Second, create a box plot for caloric intake of hypertensive and another box plot for caloric intake of non-hypertensive. The first part of the question will be addressed by Mr. Sai Kumar Kuneti, and the second part of the question will be addressed by Vibhavari Gadhe. Before we start solving the question, let us first look at the data. The name of the CSV file is caloric intake and blood pressure. It has two columns, caloric intake, systolic/diastolic.
So first part of the question is do a chi-square test to see if caloric intake affects systolic blood pressure. So first let us know what is chi-square test to just have a brief idea of what it is. The chi-square test is a statistical method used to assess relationship between categorical variables. It determines if the significant association between observed and expected frequencies of category in a contingency table, indicating whether variables are independent or related. There are three main steps in completing the first part of the question. It is reading the data pre-processing, and performing the chi-square test.
First, we read the data. The code starts by loading necessary libraries ggplot and readr, which are used for data visualization and reading the data respectively. It reads the data frame from the file caloric intake and blood pressure.csv into a data frame called df. Next important step is data pre-processing. Before this step, I have used strdf command to display the structure of data frame df. This helps us understand the variables and their types. In the data pre-processing, the data which we have has a combined column named systolic and diastolic, contains combined values of systolic and diastolic blood pressure separated by a slash. The code first splits the combined values into single values by using command str split and sapply. Using this split and sapply, we have divided we have divided columns into two separate one combined column into two separate columns, systolic and diastolic. A new column named caloric category is created to categorize the caloric intake into overindulgence and normal based on their threshold of 2500 calories. Another new column named systolic category is created to categorize systolic blood pressure into hypertensive and non-hypertensive based on the threshold 130 mmHg.
Next step is processing is performing the chi-square test. To perform a chi-square test, first we have to create a contingency table for the caloric category and systolic category columns, which we have created earlier in data pre-processing. This code constructs a contingency table to analyze the association between caloric intake categories, which are overindulgence versus normal, and systolic blood pressure categories, which are hypertensive versus non-hypertensive. This contingency table, this is the contingency table which we get. This contingency table summarizes the frequencies of different combinations of these two categorical variables. And after getting the contingency table, next step is performing the chi-square test. Here we're using chi-sq.test function to perform the chi-square test.
This chi-square test helps us determine if there is any statistically significant association between the two categories. Here's the printed chi-square test results. This whole code reads the data on caloric intake and blood pressure levels, pre-process the data by creating categorical variables, which we have done, performs chi-square test to analyze association between caloric intake and systolic blood pressure. It helps to answer the question by statistically testing if caloric intake affects systolic blood pressure. The test statistic we obtained is x squared is equal to 7.0715. This value tells us how much the actual data differs from what we would expect if there was no relationship between caloric intake and systolic blood pressure. The DF degree of freedom for this test is 1. This indicates number of independent pieces of information used to calculate the chi-square test statistic. P-value is 0.007832. The p-value tells us about probability of obtaining a test statistic as extreme as or more extreme than the one observed if there was no relationship between caloric intake and systolic blood pressure. Since p-value is 0.007832 and less than the significant level, assuming 0.05, we reject the null hypothesis. This means that there is statistically significant relationship between caloric intake and systolic blood pressure. In other words, just to simplify, the amount of food people eat has an impact in systolic blood pressure.
Coming to the second part of the question. Create a box plot for caloric intake of hypertensive and another box plot for caloric intake of non-hypertensive. Before we start our code, it is essential for us to understand that we have grouped systolic blood pressure level more than 130 into hypertensives and systolic blood pressure less than 130 into non-hypertensives. Our aim is to visualize and understand potential differences in caloric intake patterns between hypertensive and non-hypertensive groups. To create a box plot, we will need the ggplot2 library. Assuming it is installed in the last week's assignment, we will now run the ggplot2 library. The boxplot function in RStudio is used to create box and whisker plots, providing a visual summary of the distribution of a dataset. Inside the boxplot function, we pass the argument formula, the formula specifying the relationship between the variables, in this case df $caloric.intake, which is the dependent variable, tilde, which signifies the relationship, df $systolic category, where systolic category column is the independent variable. Note that the column name in our original data is caloric space intake, but while passing the argument, we write df dollar where dollar sign indicates column in R, df $caloric.intake. It is because the name of a column in the df data frame when we read the CSV file is caloric.intake. Thus, it is always advisable to print the data frame before we start coding. So now let's read the CSV file and print the data frame. As we can see here, the name of the columns are caloric.intake and systolic.diastolic. Coming back to our box plot. xlab stands for x-axis label. It is an argument in the boxplot function that allows you to specify the label for the x-axis. Here it is blood pressure category that indicates a systolic category where we have grouped into hypertensive and non-hypertensive. ylab stands for y-axis label. Here it is the caloric intake. Main is equal to boxplot of caloric intake is the title of the boxplot. COL stands for color. It is an argument in the box plot function that allows you to specify the colors for different categories. Here light blue is used for hypertensive and pink is used for non-hypertensive. Why? Because the order of levels for DF dollar systolic category is such that hypertensive comes before non-hypertensive. Therefore, light blue is associated with hypertensive and pink is associated with non-hypertensive. Let's print our DF dollar systolic category. And here when you see the levels, hypertensive comes before non-hypertensive. Unlike some other plot types, the box plot function generates a graphical output directly. Therefore, it does not need the print function. In line graphs and scatter plots, the AS function, that is the aesthetic mapping, is often used to specify the variables for the x-axis and y-axis, as well as additional aesthetic properties. But for the box plot function directly takes a formula to specify the relationship between the variables. Now let us plot the box plot. And here it is. Let us now analyze the box plot of calorie intake versus blood pressure categories. There are two blood pressure categories, hypertensive and non-hypertensive. The blue box indicates hypertensive group and the pink box indicates non-hypertensive group. The lower end of the whisker in the box indicates minimum calorie intake and the upper end of the whisker indicates maximum calorie intake. Q1 is the first quartile and Q3 is the third quartile. The difference between the two is the interquartile range. In the hypertensive group, the minimum calorie intake is 2700, maximum calorie intake is 3500. The first quartile is 2800, third quartile is 3200, and the median, which is the dark line in the box, is 2820. There is 25% of data between minimum and Q1, and there is 25% data above Q3. Between Q1 and Q3, there is 50% of data. In the non-hypertensive group, the minimum calorie intake is 2000, maximum calorie intake is 2800, the first quartile is 2300, third quartile is 2600, and the median is 2450. Now let us draw inferences from these values. The range of caloric intake in the hypertensive group, that is from 2700 to 3500, is wider compared to the non-hypertensive group, which ranges from 2000 to 2800. This suggests that there is a greater variability in caloric intake among individuals in the hypertensive group. The median or central tendency indicates that in caloric intake for the hypertensive group, which is 2820, is higher than that for the non-hypertensive group, that is 2450. This indicates that average individuals in the hypertensive group tend to consume more calories than those in the non-hypertensive group. The interquartile range for the hypertensive group is 3200 minus 2800, that is 400. And the interquartile range for the non-hypertensive group is 2600 minus 2300, which is 300. The hypertensive group has a larger interquartile range, reinforcing the idea of greater variability in caloric intake. Points beyond the whiskers are considered outliers and they can affect the interpretation. There are no outliers in this box plot. Overall, the box plot suggests that while the median caloric intake is higher for hypertensive group, there is also more variability in the caloric intake within that group. The non-hypertensive group, on the other hand, has narrower range and lower median, indicating less variability in caloric intake.